we're just a couple minutes late, so let's get started. So I've updated this archive. So just grab this folder. Apparently one person last week had some error unzipping this file on a particular Mac system, but no one else had any issues, right? Unzipping this. Okay. So this is where we are. So let's see, we should start from I think last time were we at 04? I'm not sure. Because we were, yeah, sorry, a bit short. So, so last time, oh yeah, right, we were at list comprehensions, right? So I'm going to get a bit more into anonymous functions, I think. So we define probability axiomatically, conditional probability, and then sort of using yeah, we went through for loops, conditional statements. We were somewhere here, right? And then the idea was using these classes for probability maps and random variables. We were able to do product experiments quickly. So it was essentially tossing a coin multiple times, for example. So any of these small discrete experiments, the classes were implemented so that you could do various methods on them. And I said you don't need to understand classes in Python. It's just to illustrate that we can go from a mathematical concept to some kind of a program that implements it quite easily. And then we got into list comprehensions. Right, where were we? Conditional list comprehensions. Did we do nested list comprehensions?
Did we do list comprehension?
Oh, we did not?
I don't think we got that. If I remember correctly.
Okay, I don't know where you were, where we were. Okay, let's start. I think, yeah. Should we start with list comprehensions? So this is basically, you know, functional programming in some sense in Python. Okay, so basically, this is a very powerful feature in Python, and yeah, sure. So let's say we define a list called, you know, my list, range 0 to 9, and then we can just square each element in the list by simply doing this. We can just say, you know, it's like a for loop, except now we have a list and we say x squared for x in my list. So it'll basically go through every x in my list and then do whatever you want it to do. Right? So we're just squaring every element, and that's my new list. Okay. So so you can do list comprehension in tuples as well. So here, you know, instead of the usual for statements, now we have this list, the beginning list, you see the outer wrapping list, and then we have a tuple here, x comma y, right? And then we're saying x is going to go through a for loop in this list, 1, 2, 3. And again, we have another for statement for y is going to be going through this list, 3, 1, 4. And then we also have a conditional here, if x is not equal to y. Right, so this is a nice way of getting the unequal elements, right? So you can easily create tuples under some condition. So this is called conditional list comprehension, right? So what we've done above is just exactly this. So if you think about nested for loops, so we can do the following. Say, let's say coms is some empty list, and then the outer loop is going through 1, 2, and 3 for x, and the inner loop is going through the elements 3, 1, and 4. Is that too small for you? Maybe you should sit forward, because if I make it any bigger later on, the images won't be, the interactive images won't work.
I'm just thinking, this is not the same for a log tree.
I don't know. I'm kind of on a groundhog day here, so someone told me they haven't seen this before. Did we see all this?
It's not the regular.
Oh, right. No, sorry. You have to update the content. Just, yeah, replace all the notebooks with the new. It's just jazz. Okay, so I've changed a few things here and there. So this is your latest content. And we'll do one more update a couple minutes before next week, and I'll be done. Yeah, so just go to this new folder. Right. Yeah, so that's basically what's happening here, right? And then I have a conditional statement. If x is not equal to y, then we use the append method. So we append these tuples, x comma y, as a little tuple with parentheses, to coms. So now it's exactly, this is equivalent to what we did here, except what we did upstairs is nice and simple, right? It's once you get used to it, list comprehensions can be very powerful. So here is again creating a list of two tuples. So now we want the number x and its square. So we can use star star for Python square, or just use SageMath square. You know, this is the thing. Okay, so it's very handy if you want to plot x and f of x as a pair of points, as a list of two tuples of points. Also, flattening a list using list comp is also straightforward. So let's say we have my list of lists, which is the list containing the list 1, 2, 3, and the list 4, 5, 6, and the list 7, 8, 9. Then I just am going through num for each element in my list of lists for each num in the element, right? So that means I'm just, walking through each list in the first list of lists, and then for each of those lists, I'm walking through each element in that list. Right? So this is also very handy. Are there any questions about this basic idea? Okay. Yeah, and we saw conditional list comprehension already. That's exactly what this is. Looking at the odd numbers and the even numbers, for example. So let's do a little utry modified in Excel to output x cubed for each x in my list. So that's all we have to do. And that doesn't work. Oh, nice. Yeah. Okay. Yeah. So, okay, so let's declare my matrix to be a list of lists. Okay, this is just, yeah, so I'm defining my matrix. Then I want to basically walk through each row in my matrix. That's what this first list is doing. This list itself is a list comprehension, right? And then I'm going to grab the ith row of that matrix, where I is coming from outside, right? I is just going to be 0, 1, 2, and 3. Range 4. Yeah. Yeah. Yeah, so this is because we're getting the transpose this way. Okay. Of course, for matrix operations, we will use NumPy and other libraries optimized for scientific computing floating point values for matrices. Okay, the above thing is exactly equivalent to this one. So what are we doing? We can create an empty list, and then for I in the number of columns, 0, 1, 2, and 3, I'm going to simply append the rows, right? The ith row for each row in the matrix. Okay, are there any questions about the sort of mechanics of list comprehension? So then there are these sort of words called anonymous functions, right, and lambda expressions. So this is once again what list comprehension is really doing for us. So anonymous functions are basically functions not bound to a name, right? When we use def and gave a name for a function, that's bound to the name. But anonymous functions are generally not bound to a name, and they can be used immediately in expressions, right? And usually they can be too complicated. The way you do it is by using what are called lambda expressions. Yeah, and this is essentially what we do. The lambda expression essentially is mimicking this typical function, the named function, right? So, and the way the syntax for lambda expression works is this keyword called lambda, and then it'll have arguments, and then after that you put a colon, and then the little expression that we want this anonymous function to do. So it's like the body of the function. Okay, so in fact, this list comprehension we just did earlier is the same as this mapping of this lambda expression. So we have to map this lambda expression to each element here. And in fact, people who like to learn or do Apache Spark through Python use a lot of lambda expressions, okay? Because they don't have the nice Scala syntax for say various maps and the closure. So you have to use this lambda keyword all the time, and then Apache Spark basically writes the Scala code for you and executes that under the hood. So we won't use lambda expressions because apparently list comprehensions are better than lambda expressions according to the programming guides, Python. Okay, so we're going to use list comprehensions heavily, and we'll visit a bit more functional programming soon. Okay, so this is our next stopping point. Yeah, if I don't have enough content for the rest of today, I'm going to just do Blackboard lectures. Okay? I'm sick of programming, actually. I mean, it's nice, but it's just. All right, so let's see how it goes. So this is the main topic. So we're going to cover random variables a little bit more, and then these notions called expectations of random variables. And then we'll formally define data, and data space, and statistics. And then we'll revisit arrays, tuples, and more subtle notions from functional programming called iterators and generators. So Tilo is here because I thought I might collapse this morning because I had a really bad hay fever the last few days. So, but I'm fine, I think. Yeah, so here is the list of topics. So we'll get into continuous random variables, expectations, data stats, and then these are specific kinds of statistics, examples of statistics called sample mean, sample variance, order statistics, frequencies, empirical mass function, empirical distribution function, and then we'll do a live data ingestion and sort of do try and catch on the fly as things break. Yeah, and this is the New York Powerball data set we'll fetch from New York. And then, yeah, we'll get into more subtle details of arrays, tuples, iterators, and generators. Okay. So recall that a random variable from last week is simply a mapping from the sample space capital omega to the set of real numbers R, right? And why do we need it? Because we want to use arithmetic, right? So, so this is basically the picture we have is there's some sample space omega, something happens in nature, and we're interested in, and then there is, you know, okay, so let's recall. So this thing is, so each little thing is called little omega, another one is called little omega prime, right? Let's recall, what is this? This is a set. What is a set? It's a collection of distinct elements, right? And there are countable sets and uncountably infinite sets, all of that. Then we basically said that there is this, so this is called sample space. Okay, what are the other notions we need for probability? So there's some subsets, right? Right? Subsets of the sample space. What is the word for these subsets? Event, right? So let's write down in maybe this order. So we have events. So events are essentially a subset of the sample space, each event. But then there is something more special about the events, right? So if the events satisfy certain properties, then that collection of events over the sample space is called what? So sigma algebra, remember? So we call this to be script f of omega. So that is essentially a certain collection of events, subsets of the sample space, that have to satisfy certain properties, right? What are the properties that they should satisfy? And the reason we want them to satisfy that property is why? Because we are defining something called probability, right? That assigns values in the unit interval, right? And that probability is a function whose domain, right, is the sigma algebra, right? And that probability had some axioms it had to satisfy, right? Okay, so let's go back to Kolmogorov, right? So what are the axioms for probability that, you know, that motivate probability?
We must add to 1.
Okay, so yeah, so the probability of the entire sample space is 1. So something happens. That's what that means, right? So which immediately means that omega should be an element of the sigma algebra over it, right? Okay. You agree? Yeah. So then what is the second axiom? I actually don't remember, right? Just build it. Because you're not supposed to memorize anything. Otherwise, you know, it's not maths, right? Yeah? Right. Yes, okay. So should we put that, what should we go first here?
So, P of A complement is 1 minus P of A.
P of A. Is that a property or an axiom?
I don't know, it's just the definition of the sigma algebra.
Yeah. Okay, so so if A is in omega, then okay, if, right? Then A complement is also in F. But what is the second axiom? Is that the second axiom? No.
something with unions, but I can't recall exactly the definition.
It depends on when you ask Kolmogorov.
Oh, that's okay. Let's not go there. I just read his little book on my shelf, the one from 1930 something. You know, the one.
Yeah, but I think then that's finite rather than
Oh yeah, no,
yeah.
we're happy with finite.
Okay.
Well, sigma algebra also is the same for finite. Yeah. All right, that's good. So what is the second axiom? You can look at the notes right now. Yeah.
Maybe two sets are disjoint. The sum of the.
Oh. Right. So. Okay. So if if A intersection B is empty, is this what this axiom is saying? Probability of A plus probability of B is probability of A union B. I mean, you guys have to really give me the axioms in the right order. Otherwise, the problem in maths is I can just bring the properties into axioms and derive the axioms as properties. Right?
Yeah, and so there are so for any event A, it must be between 0 and 1.
Yeah. Okay. So probability is going to be always okay. This is good. So the probability is always between 0 and 1. Okay.
And then this joint one, and then you have this infinite sequence of pairwise disjoint events.
Okay, so this is 1, that's 2. Is this 3?
That's yeah, that's 3.
Okay, good. And then 4 is this really weird one, right? Because now we just say there is countably infinite events and all this. Okay, right. So this means if you have you know, pairwise disjoint events, A1, A2, and so on, then the probability, then this implies that the probability of the union of the ARs is equal to the sum of the probabilities, right?
And you should flip 1 and 2 there, right?
1 and 2.
Yeah, so number 1.
Oh, okay, good. All right, that's good. Yeah, thanks. Okay, that's the axioms, right? So now, yeah, see, then the complement thing is a property, I believe, right? Didn't we get that as a property? So, you know, the property was like this, you know, probability of A complement is 1 minus probability of A. Okay, so, yeah, so it's closed under complementation. It's actually closed under countable unions is the main thing, so right? So yeah. So if A1, A2, and so on belong to F, then this implies that the union of the AIs is also in F. Okay. Okay, so so these little sets I'm drawing are like my A1, A2, and so on, right? There's a whole lot of them, okay? You can't. So then probability acts on these things, right? And they give values in 0, 1. Now, that's fine, right? That makes sense. And you can do a lot with this without ever going into, you know, anything more, more than this. But the problem was this was limiting, right? Because if we wanted to actually measure something, right, we like to maybe use the number system, right? That's where random variables came in, right? So so there's this probability. So then we define the probability space as this, right? Omega, f of omega, and p, right? That's the triple. It's called the probability space. So that's in the hood, right? This is kind of in the backdrop. And then the random variable essentially is some capital X, right? That takes values. If it's a real valued random variable, it will take values in R, right? And that's what we've been looking at. And I mean, it could be something else, right? It could be a It could take values in the set of trees, for example, right? Set of binary trees. I mean, we are not doing this here, but we could. And so on. So there's a whole space of trees. One could have, I don't know, X take values there if you want. But usually we don't do that because, because it's nice to work with numbers directly, right? And X could be a vector, right? It could take values in R2. So just R cross R, the plane. It could take, So we will get into this later on by downloading earthquake dataset from New Zealand, where one of the main things is the latitude and longitude of the epicenter of the earthquake, and also the magnitude of the quake, and so on. So it's like several thousand, 20,000 earthquakes in the last year in New Zealand, for example, because it's in the Ring of Fire. So that's a very natural way to measure location. Okay, and then what's the most important thing about the random variable X? How do we talk about, how do we assign probabilities to the random variable X?
PDF or CDF?
Yes. Well, so yeah, so PDF is a bit dangerous. So the main thing is distribution function, right? DF, which is cumulative distribution. You just call it distribution function. This is very nice. It works generally for any real-valued random variable, whether it's discrete or continuous. So the distribution function was what? How do you actually? What is a distribution function? Distribution function of a random variable X. What was the notation for it?
Capital F.
Yeah, capital F of lowercase x, right? And lowercase x is a realization of, it's a real number of the random variable, right? So every time you repeat the experiment, you could take different values. So what is the definition of the distribution function? You're really, really good. You put a colon before the equal to, because this is, the left side is defined to be the right side. So what was this? Yeah, it's the probability that the random variable capital X is less than or equal to this. So we're kind of capturing the heart of this probability map acting on capital omega up to measurements of a real valued random variable, right? So that does everything, right? And then we said, look, what does this really mean? This really means that I'm interested in the probability of, so I have to basically, to find out the probability here, so some lowercase, so let's say it's in 1D. So some lowercase x happens, whatever it is. Something happens here, and let's see. So then I'm interested in the probability that, that the random variable takes any value less than this, right? So, whether it lands here or here or here, it should be the probability of interest to me, right? Which means that if I look at the inverse map, right? Remember we looked at x inverse, square bracket, of minus infinity to x, right? This half open interval. So I have to look at the set of all little omega such that the random variable x can fall anywhere in this half line, right? The probability of that is well defined and specified by p. That's what the distribution function is. So once you know this for every x, we're done, right? So this is how we, right? So we did this. It's the probability of the set of all omega such that x of omega is less than or equal to. Okay, so you need to keep all of this stuff together. Yeah. Okay, so that was random variables. Did I miss any basic points?
Did you break it, mine?
No, we do break at 10.
Just
Oh, yeah. We're just getting started. So anyway, that's just recall, right? Okay, so and then we saw this particular random variable called Bernoulli theta random variable, right? Which takes values in just 0, 1. So that's a real valued random variable. So it either takes value 0 or 1. And remember, that was a very nice random variable because it allowed us to talk about the indicator function of some set. So I'm going to say, here's my special set, A, whatever. Will it rain in the Southern Alps tomorrow? Or this capital Omega, I said, is basically the entire history of the universe, pretty much. Then I want to know whether that happens. So I encode it as 1 if it happens, or 0 if it doesn't happen, so anything else happens. That's basically the indicator random variable, it's sort of attributed to this guy named Bernoulli. Done a lot of basic work in Bernoulli. So, and then the Bernoulli random variable had this parameter theta, right? Which is, all we know from probability is that this is just some number between 0 and 1, and its complement is 1 minus that. So we pretend that, we don't know the probability that this will happen. So we call that parameter theta, which is just a number between 0 and 1. And then now we have a so-called parametric family of Bernoulli theta random variables. So often we want to infer theta. Maybe toward the end of today or definitely next week, we'll start doing full-on inference. Okay, and then the other random variable we saw was this other real-valued random variable where instead of just 2 outcomes, we had countably infinitely many outcomes, right? And that was the number of tails you see before you see a first head when you're tossing a coin again and again, right? That's the geometric random variable. Okay, now we want to start looking at random variables that are not just finitely many or countably infinitely many real numbers as their realization, but uncountably infinitely many real numbers as their realization. So that's continuous random variables. Okay, so that's the volume of water that fell on the Southern Alps yesterday. See video link below. I have no idea what that is. Sorry. I think that's some typo. So vertical position above sea level in micrometers since the original release of a pollen grain at the headwaters of a river. Well, this is a pretty beautiful experiment, right? If you can imagine. So you just drop a pollen grain and then it goes, there's going to be so-called Brownian motion, and of course the river itself has its own drift, which will be completely unpredictable and chaotic. And then the only thing you're tracking is how far above the sea level is that pollen grain at any given time, right? So that's definitely a continuous random variable that we're keeping track of in continuous time, so it's even more messy. The resting position in degrees of a roulette wheel after a brisk spin. So now, you assume you can, measure it's a continuous